You're sitting in the passenger seat of a car, moving at highway speeds, watching a high-definition video on your phone. You enter a long concrete tunnel, and the cell service indicator on your screen plummets. Logic dictates that the video should freeze immediately and display a buffering wheel. The signal is dying, so the data should stop. Instead, the video usually keeps playing. The image might become blocky and pixelated for a few moments, but the audio and video continue without interruption. This happens because we tend to misunderstand what the play button actually does. Tapping play does not trigger a single continuous transfer of a massive video file from a server down to your device. That process is called downloading, and it requires copying an entire file intact. Cell networks are highly volatile physical environments. Walls, distance, and moving vehicles cause your available bandwidth to constantly rise and fall. If a platform attempted to force a multi-gigabyte media file through that fluctuating connection, the transfer would bottleneck and fail entirely. Delivering a flawless viewing experience doesn't require a perfect, unbroken internet connection. It requires an engineering architecture built entirely around the assumption that your connection will constantly fail. To see how that works, we have to look at the server side of the platform, starting the moment a content creator uploads a heavy, uncompressed 4K video file. That high-resolution master file is routed immediately into what is known as original storage, a secure blob storage database designed for massive binary files. The viewer will never actually interact with this original file. Instead, the platform runs the file through a backend process called video transcoding. This solves two problems. It converts the file into formats compatible with thousands of different web browsers and mobile devices, and it optimizes the data for varying network speeds. This system architecture diagram maps out the upload flow. We see data moving from original storage down into transcoding servers. Here, the first step chops the massive video file into tiny, independent segments, typically a few seconds per chunk. The servers then process those chunks, generating multiple distinct versions of each one. They encode a high bitrate 4K version, a standard 1080p version, all the way down to a low-resolution, highly compressed 480p version. As the diagram shows, these processed files are then sent into transcoded storage. The final output of the transcoding process is a master playlist. A single movie has been dismantled and reassembled into parallel tracks of varying quality and weight. Long before you open the app, the system has already dismantled the media and generated a massive menu of quality options to suit whatever network environment you happen to be in. But this introduces a physical logistics problem. If your phone needs to constantly request and receive these tiny chunks of video every few seconds, the data has to travel fast. If the central database is in Tokyo and you are in New York, the speed of light itself causes a delay. The solution to geographical distance is a content delivery network, or CDN. A CDN is a global web of geographically dispersed edge servers that cache, or temporarily store, static content. This chart clearly illustrates the latency reduction. A client device requesting an image from a distant origin server faces a 120 millisecond delay. By routing that same request to a local CDN node, the delay drops to just 40 milliseconds. This flow shows how nodes get populated. User A requests an image. If the CDN doesn't have it, it fetches it from the main server, delivers it, and stores a copy locally. When user B requests that file, the CDN serves it directly. By pushing all those transcoded video chunks to edge servers sitting in your specific city, the platform eliminates major transit delays. The data is physically close enough to your device to sustain a rapid back-and-forth conversation. Looking at this high-level streaming diagram, we see the final critical link in the chain, the direct connection between your device and the CDN cloud. When you hit play, your video player software becomes an active participant. Every few seconds, it measures your device's available download speed and processing power. This real-time negotiation is governed by a standard called adaptive bitrate streaming. It is a continuous feedback loop between the demands of your phone and the menu of video chunks waiting on the server. Under ideal conditions, your phone detects high network bandwidth. It looks at the playlist and confidently requests the thick, heavy chunks of 4K video from the CDN, delivering a crisp image to your screen. But the moment you drive into that tunnel, your available bandwidth drops. Your phone immediately detects the bottleneck. Before your current buffer of video runs out, it alters its request, asking the CDN for the thin, highly compressed 480p chunks instead. The industry uses specific protocols to manage this data transfer, like MPEG- or Apple HLS, which dictate the specific video encodings and rules for different playback players. However, the core survival logic remains exactly the same. What feels like an unbroken stream of high-definition video is actually an illusion. Flawless streaming is just a rapid, ongoing series of calculated compromises, where the system happily sacrifices image quality to ensure the video never stops playing.